let's do problem 11 now. It says, your town is installing a fountain in the main square. The water is to rise 25 meters above the fountain. How much pressure must the water have as it moves slowly toward the nozzle that sprays it up into the air? So let's do this. I'm going to draw a pipe. And this is the little nozzle where it's going to spray up into the air. So essentially we've got water moving through this pipe, and it's such great pressure that when it encounters this little hole, it squirts up. Of course, this is kind of a nozzle to help funnel it. It squirts up 25 meters into the air, and then it sprays out. Right? So this height here is 25 meters from top to bottom. Now, how can we handle this problem? We know we will probably use the Bernoulli equation. So let's write it out here. So we got a constant is equal to pressure plus 1/2 rho v squared plus rho g h. And down at the bottom here, we're going to call this, here's our height. It's going like that. So our height is at 0 down at the bottom. And we can say that at the top, we're at 25 meters. The pressure at the top, we're going to say, is gauge pressure of 0. Now, one thing I haven't really talked about is the difference between gauge pressure and true atmospheric pressure. So I should probably talk a little bit about that. When you read a gauge, we often want to consider the air around us as having, that's pretty much normal. So we'll call that 0. In actuality, we have that big column of air up above us, and that presses down on us. And so by the time it gets to us, that column of air, it truly is at 100, well, just about 100,000 pascals. So we do feel some weight. That's the true pressure. Or we do see, I should say, we do feel pressure, and that is the true pressure is 100,000 pascals, give or take. And it's going to go up or down depending on the atmospheric conditions, because if it gets low pressure, then air will rush into this area because it's low pressure and it's like a little vacuum. So we'll feel winds as it blows in towards us. But if we want to, we can just define whatever this average pressure around us as being 0, because that's usually, we don't even think about it, and then that's gauge pressure. So then we could say when we're squeezing, or if we're experiencing something up above this atmospheric pressure, we would just measure what the difference is from one atmospheric pressure. So let's say that I put you in a tank and you went down, and then you would be at twice atmospheric pressure, 2 times atmospheric pressure. So I could say that you're 1 atmosphere above 0 gauge pressure. If I said it was 3 times atmospheric pressure, true atmospheric pressure, that would then mean you would be 2 atmospheres above gauge pressure of 0. So at any rate, if water is to rise 25 meters up above, then we can say, let's see, we're going to have a gauge, we're going to be sitting up here. Normal atmosphere is, we're going to call it gauge pressure of 0, so this will be 0. What's the velocity of this? Well, we're going to say it's come up right at the top. It's absolutely not moving at all, so we're going to put the velocity as 0, and we can find the constant by just plugging in rho gh. So let's do that. The constant is equal to 1,000, and then times 10, which is g, and then times h, and they say h is 25. So the constant is then going to be, what, 10,000 times 25, so it's going to be 250,000, well, actually be units in pascals, so pascals, if we want to, and that is equal to our constant. So now what we can do is go down the streamline. Everything is all connected down into here, kind of like sap in a tree. And at this bottom point, if we apply the equation again, let's do that. We're applying it again. C is equal to, whoops, no, let's get a different color. Okay, so we'll go green. And we'll say that C is equal to P plus 1/2 rho V squared plus rho GH. So now, what is our H? H is 0. So plug in 0 here, and it makes the whole thing be 0. What's the velocity? Well, we say this water here is moving pretty slowly. I know it's kind of a little bit of a kludge, but it works. So that means that the pressure down here is just equal to the constant. Oh, okay, we know what the constant is. It's 250,000. And that's equal to the pressure that we need to have in that water so that it'll spray 25 feet up into the air. Now let's go over and do problem 15 out of your book. So we've got, to dive far below the surface of the water, a submarine must be able to withstand enormous pressures. At a depth of 300 meters, what pressure does water exert on the submarine's hull? Okay, well, we'll go back to our old friend, the Bernoulli equation. C is equal to P plus 1/2 rho V squared plus rho GH. This one's a little different. And trust me, on the tests, I will give you something that's pretty similar to one of these problems that you've gotten. So let's say we're at the top of our surface, water, that was a little wave right there. Okay, and down below we've got our submarine puttering around down here, looking like a typical submarine. I don't know, this doesn't look like a submarine that I'm familiar with. Okay, I can't resist putting an eye there. Okay, so, and we know that it's 300 meters deep. That's the height of that thing. H is equal to 300 meters. Well, if we define things the way we normally do in the real world, up is positive and down is negative. So our height is actually minus 300 meters. And we're going to say that pressure is equal to 0 because we're just going to assume gauge again at the top of the water. And down here we don't really know what the pressure is. So let's see if we can figure that out. So first off, we know that anywhere on the streamline, that is that connected stream of water, anywhere in that streamline, everything's got to always sum to the same constant. So let's take the easiest point right there. At that point, let's see, what's the velocity? 0. It's not going anywhere. What's the height? Well, it's 0, right? Because we're defining this to be 0 height. It's going down. So we can say that the pressure is 0, so our constant is 0. Okay, that helps. Now let's try, oh, do you hear that? That's like in the distance. I'm in San Francisco, so there's a wonderful tugboat tugging away and making tugboat sounds. So here we go. We're going to write C is equal to P plus 1/2 rho B squared plus rho GH again. Now we'll say, okay, we know the constant is 0. What's the pressure down here? Huh. Well, the pressure, well, we don't know what it is. But we do know it's not going anywhere, so it doesn't have any velocity. So then we'll say plus rho GH. Okay, so we got that far. So now let's see, let's substitute in here. We'll say pressure plus, well, rho is 1,000 times G, which is 10, times H. H is minus 300. Oh, okay. Well, let me see. That means that we can rearrange and we can say the pressure is equal to, let's see, 10,000 times 300. And so that is on the order of 3 million pascals. Give or take a little bit because we didn't use our 10,000. And so that's how we could determine what the pressure on a submarine would be. Now let's do one of the, just a very nice example problem that deals with buoyancy effect. So we did a number of them in class, but here's a few more just so you get a little better feel for them. So we've got a nice tank of water, and we submerge in it at, let's see, an 8-kilogram log, but it displaces 10 kilograms of water. So we'll go like this. We'll plank that in. Now the water that would have been there, what would have been, water was 10 kilograms. So there's two main questions I can ask, and they're about very different things. One is, what buoyancy force does the log experience? And the second one is, what is the total force, total or net force on the log the minute you let it go? So there, you're going to get two different answers. So when you read the questions on a test or quiz, make sure that you figure out which one I'm asking. And once you know, it's really easy. So first off, what we'll do is we'll say, what is, let's see, I'll turn green now. You have to, the first step is always, what was the weight of the water that used to be there? To be there. Or you can say the displaced water. So in this case, you can figure out pretty easily what it is. Here's the water. They say it's 10 kilograms. 10 kilograms times 10 meters per second, and that means it was 100 newtons. That's what the water that would have been there would have weighed. Now notice, I gave you this in kilograms, but I could have just skipped a step and given it to you in newtons, and that's what you really needed anyway. So, oops, you're seeing what I'm going to do up ahead. Can't do that. Peek down. Okay, so let's, so we know now that the weight of the water that would have been there is 100 newtons. So the water must have been, that's around it, must have been pushing up with a buoyancy force of 100 newtons. So one, or, well, I don't know what I'll call this, but, well, I'll just call it the answer to one. One is 100 newtons is the buoyancy force. Now, the weight of the log, so let's change colors here. Weight of log is 8 kilograms times 10 meters per second, and that's going to be 80 newtons. So the actual weight of that log is 80 newtons. So altogether we can go like this. Here's our log. It's looking forlorn and gray, but that's what it's doing. Now, the weight of that log is 80 newtons. The buoyancy force experienced by that log upwards is 100 newtons. So, the total force, or net force, on the log is 100 up minus 80 down, and so clearly we're going to get 20 upwards newtons, and that's the total force that's experienced by the log. Now what we've got is problem 7 for your reading pleasure, or listening, or watching, I guess, pleasure. So your boat weighs 1,200 newtons. It's on the lake, and here's our boat. Russian boat story here, but I won't commit that to video. So we've got our boat, and it weighs 1,200 newtons. Okay, now, so this is weighing 1,200 newtons, and if that weighs 1,200 newtons, then we know we've got a buoyancy force of 1,200 newtons holding it up. So now they're asking how much water will it displace. We know that it's 1,200 newtons, and take a look at this. I'm gonna put, let's say that boat kind of went like that. This is the water it actually displaced. Now, however much that water was, clearly this is 1,200 newtons that was holding it up. So it must have been 1,200 newtons of water. Well, 1,200 newtons of water, M times G, right? That's its weight. So we know what G is. It's just 10. So we can say 1,200 newtons is equal to M times 10. And then we just divide both sides by 10. And we have 120 newtons, or sorry, kilograms is equal to the mass of the water that the boat is displacing. So let's look at a question that asks, why are failures in dams more likely to occur closer to the bottom of a dam? Well, if you look at something like, let's look at something like this. Here's Hoover Dam, and we got our water backed up behind it, and it comes out down here at the bottom through some little sluices and so forth. So here we go. We got this great big tall dam, and with all this water, And they make it thicker. Why? Because the deeper you get, the more there is weight of the water above it, and the higher the pressure. So down here, just as with the submarine problem, you have higher pressure. So breaks in dams are much more likely to occur closer to the bottom of the dam because that's where the high pressure is. Now let's look at exercise. Whoops. Exercise number 27. And it says you can inflate a plastic bag by holding it up so it catches the wind. Use Bernoulli's equation to explain this effect. So we'll get our old friend back here. And rho v squared plus rho gh. Now, as we have, here's our bag, weird looking bag, but wind goes in, the bag's closed at the bottom, so wind goes in and it has a velocity. Now remember, all the energy remains constant. So if the velocity slows down, then what's going to happen? It's all at the same height. So we can just forget about that. Velocity slows down. If this gets smaller, then pressure has to go up equivalent to that to make sure that that energy all stays the same. So the velocity slows down, the pressure goes up. There you go. And that's why the bag, the pressure in the bag goes up. Last but not least, we can ask the same question they ask in exercise 20. Iced tea is often dispensed from a large jug with a faucet near the bottom. Why does the speed of tea flowing out of the faucet decrease as the jug empties? And in essence, we can say, okay, so here's our jug. And we've got a little faucet coming out at the very bottom. And we'll have Kool-Aid coming out. Don't drink the Kool-Aid. Okay. Now, what happens is, as the level of, okay, it's tea, it's red tea, in the jug decreases. The pressure at the faucet, right? So you don't have as much on top of it to help push it out. At the faucet, decreases. That means that the total energy of the tea passing through, so it's the C in that equation in Bernoulli. C is equal to, let's see, pressure plus 1/2 rho GH plus rho, oops, what am I thinking? Let's try this again. We're going to erase that. Pressure 1/2 rho V squared plus rho GH. So that's the constant, which is the total energy in the T. And the lower this is getting, actually, the lower the total energy in the T. And so the energy of the T passing through the faucet decreases. The T can no longer, obtain as much kinetic energy. as before, and it travels more slowly. Travels more slowly. Voila!